Hi, I'd like to introduce a new feature of Ekos called the Aberration Inspector. It's not live yet, it's still in development, but it's getting towards the sort of end of testing, etc. So I think it's a good time to introduce it. So it's not really a part of Focus per se, but it uses Focus very heavily, so it's built on top of some of the Focus infrastructure. So to get it to run, you need to use the mosaic mask. You need to specify this number here, which is the size of the tile in relation to the smallest dimension of your sensor. So if you have a rectangular sensor with different scales, this is 25% of the smaller scale. So having specified that, if you hit autofocus, which I'll do, it will run an autofocus routine as normal, but at the end of the process it will now fire up another window which will give you information about the aberration inspector. So the way to sort of set this up is to use whatever configuration of focus gives you the best outcome. So, you know, if you like HFR and in my case hyperbola, etc., then pick those parameters. I'd point somewhere where you get good focus solves, and you're going to want a lot of stars for this, so point somewhere at the Milky Way, I would suggest. The reason you want to be solving well before you use the aberration inspector is that you will need to get quality results in order to get something useful out. So as I mentioned, once focus completes, which it obviously has, it gives you this window. So just going back to focus for a second, you know, the V curve there's fine. The R squared on the focus run was 0.99. So I'd be happy with that. If you had a poor focus run, for whatever reason, I would sort that out before spending time looking at the aberration inspector. But in this case, it looks good. So let's dive into it. So it fires up, and I think the first thing you see is probably 4 sections of this window. So the first up here is a curve with a bunch of lines on it. Then we have a table of data. Then we've got 4 output fields which give information about back focus and tilt, which are the 2 things that the aberration inspector works out. And then there's a 3D graphic over here, which I'll explain a little bit more about shortly. So let's just dig into the first part, which is this series of curves at the top. So if I get rid of other stuff, it might make it okay. So as I said, this is very much like the V curve on the focus tab. So basically what's happened is each of the 4 corners and the center tile of the mosaic have been curve fitted and individually, and they're, you know, represented by the different colors, and over here there's a little legend that it gives you a 2-character acronym for the curve. So TL is top left, TR is top right, C is the center, bottom left and bottom right. So you can see on here, these are the solution points. You know, I can take the labels off. I can put the critical focus zone on just for some sort of scale here as to, you know, how far apart or how far out of the critical focus zone some of these individual tile solutions are, which is obviously quite interesting. So by changing this setting here, I can get a slightly different view. There there are 9 tiles within the mosaic, so if I want I can display them all, or there are 2 other views. There's the one I was just showing you, which is the center and the outer corners, and then there are the center again and the 4 other tiles which form a sort of an inner diamond. So I think for the purposes of this I'm going to stick to just showing you the outer corners and the center, because there's less data, but when you run it you might well want to run it with all of the mosaic tiles. So just putting that back up, now coming on to the table, if you hover over the leftmost 2 columns, you'll get a it's not a tooltip, but it's like a tooltip come up that displays a graphic of a sensor, and it shows the mosaic tiles where they fall on the sensor to scale. So I'm hovering over the top left here, and you can see the TL at the top left corner of that graphic is highlighted. So you can see, as I move down, now the TR is highlighted in its color. So you can see where each of those tiles are in relation to the sensor. And if I go back and change this, for example, and then go back again, it'll obviously position all of the mosaic tiles on there. So the other columns relate to the data from the V curve at the top. So for example, the central tile there solved at 18,008. So here in the table you can see 18,008 is the solution. Then these deltas are deltas of the individual tile, in this case the top left, versus the center. So it solved at 18,014, which is 6 ticks off. So the delta 6 ticks off the solution that the center tile solved to. So that's why the delta there is 6 ticks. This column here is the same information but in microns as opposed to ticks. So that information comes from the CFZ panel on Focus. So the step size that you can set up within CFZ specifies how far in microns the focal plane will move when you move the focus of 1 tick. So in my case, it's 1 tick corresponds to 5 microns. So I'm just going to multiply the 6 by 5 microns to get a 30 micron number there. Then you've got the R squared of the individual curve fitting for this particular tile. So these are all pretty good, 0.99 or 1. If for whatever reason there was a problem and one of these didn't solve, then the exclude checkbox would be ticked, because obviously the data is no good if it couldn't solve or put a curve through the data. If you, for instance, decided that, say the R squared was very low on this and it was perhaps polluting your results, you can just click that and it will adjust the results down here by excluding this row from the data that it uses to perform the analysis. Okay, so that's the table. The table then is analysed and it produces these 4 pieces of data. And these 4 pieces of data relate to the aberrations that it thinks is in your optical train. So it's concerned only with 2 aberrations. One is the backfocus error, and the other is to do with the tilt of your sensor in relation to being flat to the plane of the telescope. So if you have other aberrations in your optical train, they may well be polluting these results and giving you poor results here. So the assumption going into using this tool would be that you have minimal aberrations other than back focus and or tilt. So for example, if you have poor collimation, I suspect that would cause a problem with the results here, and it would be worthwhile fixing other aberrations that may affect your the quality of your imaging before attempting to use this tool. The other thing is, I think it will only work if you're fairly close in terms of back focus and tilt. So I wouldn't use this to if you're a long way out of back focus to try and get yourself correct. I think what you should do is do whatever the mechanical process is to get the right spacers and whatever to get your back focus as accurate as you think you can, and then try and you could use this tool to see if you can tweak it to get it better. So how does it actually come up with these numbers? So the back focus, if you like, is a shift of the deltas of the focus position from center that is sort of consistent across all four corners. So what's happening with if you do have a back focus error is that the Petzval surface that's coming out of your field flattener and is incident on your sensor is not flat. So if it's not flat, what's happening is that the point of optimum focus in the center is going to be different from the point of optimum focus out in the corner, and that is because either you are too near, your sensor is too near to the to the field flattener, or it's too far and it's not the flattener is not flattening out your optical image appropriately because of that. So I can kind of demonstrate that with this little 3D graphic over on the right hand side. So if I hope you can, so I just make this bigger, that would probably help. Oops. So again, there are some sliders here, so we can kind of make it a bit bigger. And so this 3D graphic shows two things. It shows the sensor and it shows what I'm calling this Petzval surface, which is, you can think of it as the surface of optimum focus. So it'll be flat if you are, if you have no back focus, but if you no back focus error, but if you have a back focus error of some sort, it will be a curved surface. So let's start off by maybe just speaking for a couple of minutes on the sensor. So if I just show the sensor there, what this graphic is trying to show is, if I put the labels on, again, this is the top left, and top right, bottom right. So I'm sort of looking at this towards the telescope, and this is the view of the sensor. Left to right is along this way, and top to bottom is along this way. 0 coordinates on X and Y and also on Z are at the center of the sensor in this diagram. Now, if I can rotate this, and we have some tilt, so we have left to right tilt of 1.5% and top to bottom tilt of 0.6. So if I put this in simulation mode, what I can do is, if I try and just straighten out this is the left to right tilt slider, so I can just swivel this round and that's about right. And similarly top to bottom I can do that. So obviously if you do have a tilt correction device like a a photon cage or an octopi, then you know what you'll be wanting to do is to use this to flatten off your you know, your sensor. Now you know, this is just like a graphic that shows you what you're trying to achieve, and I think it's quite useful for explaining things. So you know, we have if I take the sim mode off, this is how the, you know, the results have showed the sensor, a bit of tilt top to bottom, and a, you know, a little bit more left to right. So that's the sensor. If I hide that and show you the Petzval surface, now this, as I said, is a representation. I mean, you can think of this as the surface of optimum focus. Now, if you had no back focus error, I can put this back into sim mode again, then what would happen is this would be flat, which is about there. So it's basically you know, all points on the sensor would be solving to the same focus position, because the field flattener is doing exactly what it should, which is flattening out your field over the whole of your sensor. Now that would be the ideal position. Now what we have is something which is a little bit like that. Now what that means is, you know, the sensor is going to be solving at a certain position in the middle, but it's be solving at a different position in each of the corners, because this surface is curved and not flat. Now what the you know, what we need to do is we need to adjust the, you know, this back focus such that the surface flattens itself out. Now if I go too far and sort of overdo it, then what's going to happen is it's going to curve the other way, and I'm going to have an analogous problem where I'm going to be in focus at the at different points in each of the corners of the sensor versus the center. So that's the, you know, that's the surface. So if I take the sim mode off and put the sensor back on, and one of the things I like doing is using this Petzval wire, but I don't know if that's going to show up very well on the video. But we can see the intersection. Maybe I'll just put the surface on. We can see the intersection. So the, you know, this slightly darker surface is the square sensor, and then we have the curved Petzval surface. So you can see what's sort of happening here. The Petzval surface is, you know, striking the center of the sensor, but it's gone past the sensor on one side, and it hasn't quite made it onto the other side. So what this graphic is trying to tell you is that, you know, we have tilt because the Petzval surface, sorry, we have back focus error because the Petzval surface is not flat, and we have tilt because the sensor is not flat in relation to the Petzval surface. So going back over to the results again, what the results were telling us were that we need to move the sensor away from the flattener, and it's giving us a number of 44 microns. Now, the thing to probably be aware of is that that 44 microns is a measure of the back focus delta. It's not a measure of how far you would physically need to adjust back focus. That will depend on the characteristics of your telescope, and there will probably be some sort of multiplicative factor that you would need to multiply the 44 microns by in order to know how far to move the back focus. I think the way I look at this is it's a little bit like a collimation type process where you get a bit of a clue from this that you need to move the sensor away, and you have a number. I think what you're going to have to do is make an adjustment on the back focus that would move the sensor away from the flattener, and rerun this process. And if, for instance, you came up with, you know, 22 microns, then I think what you'd conclude is well, first off, you moved it in the right direction. Second off, you moved it about half as far as you should have done, and therefore you'd probably kind of repeat whatever it was you did. So if you moved a screw half a turn, you'd move it half a turn again and rerun. So it will be a sort of an iterative type process to get to whatever the best values you can for these back focus errors and tilt errors. So probably just one other thing's worth showing. I've just made this table editable for the purposes of this demo. I don't think there's any reason in a real world environment anyone will want to adjust these numbers, but it's quite interesting to do that in this demo because it can hopefully give you a bit more insight into how this works. So let's just say we had a perfect world and I set all of these to 0. Now this would be obviously aberration heaven because we have 0 back focus delta and we have 0 tilt in both left to right and top to bottom dimensions. So if I go and look over here, swivel this round, basically this is showing you that the sensor is kind of swallowed up by this Petzval surface, but fundamentally the Petzval surface is flat and the sensor is completely flat to the surface. So this would be the ideal situation that we would all want to have with our setups. Now, if for instance I put a just a positive number in here, let's say 10 ticks for each of the tiles in relation to the central tile. Now what you can see here is I have a perfectly flat sensor. There's no tilt on that sensor because all of these points are each of the corner points are solving to the same 10 tick difference in relation to the central tile, but I've created a 50 micron, which is 10 ticks in my case, back focus. So what you can see here is that the Petzval surface is incident on the center of the sensor at in this case 18,008, but we're going to have to move another 10 ticks in order to solve in each of the corners. So if I do the opposite and put minus 10 in each of these, what this shows is the analogous situation where we have the curvature of the Petzval surface the other way, and I've gone from being 50 microns of back focus delta one side one way to too far the other way. So that's back focus. If I wanted to put some tilt in to this, what I could do is I could say the top left and top right are solving at minus 10, and let's say the bottom left and bottom right are solving at plus 10. So what this corresponds to, let me just swivel this around a little bit, is we have 0 back focus now because the back focus is really just an average of each of the deltas in relation to the central tile. So in this case we've got 2 minus 50s, 2 plus 50s, so there's no the average is 0 rather. So the back focus delta is 0, so that means our Petzval surface is flat, which it is. We have no left to right tilt, but we do have 100 micron top to bottom tilt. So again, if we look at this sort of inclined plane here is the sensor, and that's showing that that is inclined to the Petzval surface, which is what the tilt is. And I could do something similar. I could say that the the left and the right are set up in a similar way. So again, what I've done here is there's zero back focus error. There's now no top to bottom tilt because the numbers I've put in have a zero top to bottom tilt, but there is now 100 micron left to right tilt, which if I swivel this round you can sort of see. This is kind of why I like just using the Petzval surface, because it's a little bit easier to see. So what I could do is, if I wanted to put some back focus in, I would just or back focus error rather, I would just add a constant offset to these deltas. So I'll just add 5, for example, so I'll make that -5, 15, -5 and 15. So in this case, we've got the same left to right tilt of 100 microns, the same top to bottom tilt of 0, but this time I've added 5 ticks or 25 microns of back focus error, and hopefully you can see that. You can see the Petzval surface there is curved. So we've now got probably the most common situation, which is we've got an inclined sensor, so there's a bit of tilt there, and we've got a bit of back focus. So I think that's kind of it. Let me just drop this back. So this is kind of early days. I think it's probably just needs a few more bugs to be ironed out on my side, and then it should be ready to go. I think probably the way this will be used, if someone does have a device for assisting with tilt and back focus, would be you'd run the aberration inspector. It will bring up this window. You'd make an adjustment on your device based on the information you've got in terms of the tilt and the back focus. You can simply just rerun focus, and it will launch another window, and then you can you can basically compare the before and after in terms of the numbers here, and you can see how the adjustments you've made have affected the tilt and the back focus. And as I've said, I think although I don't have a device that lets me do this myself, I imagine that once you've played around with it a bit, you get a bit of a handle on what you need to do with your device to flatten off the tilt and back focus errors that you'd see at the start. So that's about it. Appreciate any comments, and see you next time.